Hi everyone, this is Mr. Hall and this is a quick video about potable water. This is a topic that is on the Earth's Resources unit of the GCSE AQA. It might have overlaps with other courses which might be useful, but that's primarily what I'm aiming at here. This video is basically going to address just some of the basics about potable water. So it will talk about the definition and the description of potable water and how that's different to pure water and also saline water, which you need to know about. And I'll also describe the processes that we use to treat both groundwater and salty or saline water as well. So first of all, one thing worth mentioning, which I've discussed in previous videos, is that the Earth is running out of lots of resources, and water is one of the key resources which we're running out of. And this might be surprising for some of you, where you just turn on the tap and there just seems to be like this endless stream of water. But actually, there are other parts of the world where water is very scarce. And half of the world's population, according to some sort of professional bodies, they estimate that half the population may struggle to get fresh water by 2030, which is coming up pretty soon. So it's a scarce resource. It's a difficult one to get a secure supply of. And there are things that we can do in order to make sure that we do get a secure supply. But before I go any further about that, let's talk about the differences between fresh water, salty water, etc. So first off, let's talk about distilled water. Now, distilled water is only H2O inside it. There's nothing else. Okay, so if I was to draw a diagram, this is a box containing H2O. You can see I've only got H2O molecules there. Now, that kind of water is not what comes out of your tap. What you get out of your tap is just tap water. Now, tap water contains H2O, obviously, and it also contains other salts which have dissolved in it. Okay, so you might have some fluoride ions, and you might have some calcium ions, and you might have some magnesium ions, and you might have some other ions as well alongside that. Some of them have been added on purpose, some of them haven't, okay? And that's one type that you have. Now, they're all very different to seawater or saline water. Seawater is very salty, as you may know. Now, it contains H2O with quite a fair amount of sodium chloride, or NaCl. And inside it, you can see that you've got H2O, you've also got Na plus ions, and also Cl minus ions, to such an extent that it actually becomes undrinkable. So those are the different types of water you have. Now, that's all fine and well. But the key thing is, how do we know whether it's fit to drink? Because although we're showing the different ions, what we're not showing here are any pathogens or things like that which might cause you real harm. So that's where we get to the definition of potable water. Now, potable water is water that is fit to drink. Interestingly, only 1% of the world's water is actually suitable for drinking. And most potable water that we find is produced by a number of processes. The first thing we have to do is we have to find an appropriate source of this fresh water. Now, there's a few different sources you could find. For example, you could find it in groundwater, which can be tapped by a well, and then you bring it up, and then you can either take it to like a big pumping facility or even sort of in local homes. Also, it can be from surface water, which can be in a reservoir, it can be a lake, it can be from a river, places like that. So that's where you find the fresh water. Once you've found it, you then have to filter it, okay? Because there might be things inside it, like twigs and bits of dirt, that you don't want it to be there. So it has to go through filter beds. And this could be quite a detailed process. You don't need to know much about it. You just need to know that we filter it by putting it through filter beds. That's pretty much as you need to know. So you filter it, and that's fine, and then you sterilize it. Now, the sterilizing you do need to know a fair bit about, and I'm going to talk about that in the next few slides. So let's talk about sterilization. So the one way in which you can sterilize water is chlorination. Now, what that basically is adding chlorine to water. And if you have your own sort of water supply at home, what you could do is simply add chlorine to that water, and in theory, it should sterilize it and kill any pathogens which are inside it. Now, it's very effective. That's a good thing about it. It does kill all pathogens. The downside is that chlorine is quite toxic in large concentrations, and isn't necessarily pleasant to drink if you've got lots of it in the water. So it's effective, but it's not perfect. Now, the other type you can do is by adding ozone. Okay, now ozone is effectively O3. Okay, it's 3 ozone molecules. Don't need to know much more than that. Yeah, we say it's O3. And you add it to water. And what ozone does is quite good. It kills the pathogens, but it also gets rid of heavy metal ions. Okay, so you might have in water, so Fe3+, and You might have, I don't know, manganese 2+, whatever. You've got all these metal ions which might be in water, which could potentially cause harm either to you or to aquatic life, whatever. And what the ozone does is it removes those, which is quite good. So it's very effective. It doesn't involve adding chemicals in the same way that the chlorine does, but it's quite expensive and there are some safety concerns. Ozone is actually quite toxic. If ozone comes into the atmosphere at a low level, it can cause real harm. So ozone's not perfect. Now, the final thing we can do is add UV light. Now, UV, I'm just going to move my face, there we go. UV is a part of the electromagnetic spectrum, which you've hopefully learned in physics, and it's just after visible light, which obviously comes after infrared. So in terms of wavelength, it sort of gets a lot shorter and the frequency gets a lot higher at UV, so it's quite powerful radiation. And what you do is you direct UV rays straight into the water, and that can help kill the pathogens. Now, this is very, very effective, and it doesn't involve adding chemicals, but if you have a UV light, it's a system that does need quite a lot of maintenance, like things can break on it and so forth. So each one of these has their pros and cons. You don't necessarily have to know the pros and cons here. They might give it to you in an exam question. You just need to be aware of them and just know that some techniques have strengths and weaknesses compared to the others around it. So that's the sterilisation process. Now, there are some countries out there which they can't even find a freshwater source. We just talked about the sterilisation process, assuming you have a freshwater source. Some don't. So, if you're in a very arid region where it's difficult to find water, you have to have a source of water in order to do any sterilisation at all. Now, as I said before, saline water is water that contains salt, sodium chloride ions. Now, if it has too much salt, or if it's too saline, it's undrinkable. And that's because basically it's biology with regards to osmosis, and that's something which you've learnt about hopefully in your biology classes. Now, if a place has no access for fresh water, what they may have to do is desalinate seawater, assuming that they have a coastline. Now, there are two ways in which you can desalinate water, which is taking the salt out. Now, one of them is distillation. Now, distillation happens on huge, on an industrial scale. The image I've shown here is from a massive desalination plant in Dubai, where they do distillation on a large scale. And what you basically do is you evaporate the water and then you condense it. So if you look at this setup here, which is probably similar to what you've seen before in your science classes from a young age onwards, you apply heat here, and that makes the water evaporate and turn into a gas. And then what the water then does is that it goes into a condenser where it's quite cold, okay? And because it's quite cold there, this water then condenses and turns into a liquid, okay? And when it turns into a liquid, it drops into there, and it has no salt inside it when that happens. Ooh. There we go. So we saw that. Now, this process is really good. So you evaporate the water, you condense it, it works really well. The problem with it is that it uses a lot of energy because you have to boil all this water. Now, if you're thinking about providing drinking clean water for a whole nation or for a city, you need a very, very big plant, such as you can see in this picture. So you need a lot of energy. That energy tends to come from the burning of fossil fuels, which contributes to a number of problems, as you may be aware of. So it's effective, it works, it's just problematic. Now, the second way in which you can desalinate water is by reverse osmosis. Now, again, these happen in quite large plants. This is an image from a reverse osmosis plant in Barcelona. And what you do is you push water through a membrane and it goes against a concentration gradient. Hopefully you've learned about concentration gradients in biology. It's basically similar to active transport. So what you're doing is you're making water go from an area where there's not much of it to an area where there's more of it. So effectively it's going from an area where there's lots of salt to not much salt. So it goes up a concentration gradient. Now, because you're doing that, it requires energy. And you need a lot of energy to do that. And again, that comes from fossil fuels, which is problematic. And that's it. So I hope this has been useful in terms of your knowledge of potable water and how you desalinate it, so forth, and best of luck in your studies.